Welcome everybody to our Veolia Water Tech Talk today. My name is Jill Browning and I will be the moderator for today's webinar on removing selenium from industrial wastewater. Before we get into our presentation today, I do have just a couple quick housekeeping slides to go over with you. First of all, hopefully you should be able to hear me speak at the moment. But I do want to just briefly mention that should you have any audio troubles throughout the course of the webinar today, that we do have two different ways to connect. You can use either through your computer audio or call in through a phone line. So feel free to switch back and forth should you have any difficulties. And also, due to the large number of attendees that we've got on our presentation today, we have gone ahead and muted everybody's line. But no worries, you can still interact with our speakers. And in terms of interacting with our speakers today, feel free to ask your questions via the questions panel at any time throughout the webinar. We do have some time set aside at the conclusion of our webinar today for our speakers to answer them. So please feel free to ask any questions that may come to mind, and we will try to get through as many of those questions as time allows. Today's webinar is one of many in our Veolia Water Tech Talks program that has been happening throughout the year. If you're interested in signing up for any additional webinars, please feel free to go over to voliawatertech.com to feel free to check those out and register for any future ones. And additionally, we have gone ahead and made available our collection of on-demand webinars that we've conducted over the last few years. So you can access more than 50 on-demand webinars, again, over at that www.voliawatertech.com URL. So feel free to go over to the website and browse through the variety of different topics that are there to see if any of those may be of interest to you. One other housekeeping note that I've got is a PDF participation certificate will be made available to you at the conclusion of the webinar. You should receive that probably within 24 hours or so. So be on the lookout for that if that is something of interest to you. And at the end of today's webinar, you will receive a quick survey requesting your feedback. Should take no more than a minute or so of your time. And for those of you who do complete that survey, you'll be entered into a drawing for a chance to win a $25 Amazon gift card. So if you would be so kind as to fill that out for us, we do greatly appreciate any and all feedback. Now, before we hop into the main part of our presentation today, if you are not familiar with Veolia Water Technologies, we are a leading water and wastewater technology provider, and we offer our clients a variety of different technologies, service options, and also projects. So feel free to learn more about us over at our website, or feel free to reach out directly to me at the conclusion of our webinar today to learn more. And just want to mention too that we do support our clients throughout a variety of different markets, whether it's a municipal market or a variety of different industrial markets that you can see on the screen here, as well as some additional ones also. So doing that to help support their water and wastewater needs. So with that, I'd like to now introduce our speakers for today's presentation. Miriam de la Durante Noel is a process engineer at Veolia Water Technologies. She graduated from Polytechnique de Montreal with a degree in geological engineering. Her previous roles at Veolia have included piloting, R&D development, and laboratory studies. As a process engineer, she has the opportunity to use her competences and field experience in water treatment by designing water treatment chains for heavy industry, aiming to reach ever stricter environmental compliance. And also joining Miriam today is Marc LaLiberté. Marc is a senior process engineer with Veolia Water Technologies with a background in process engineering and chemistry. He has 40 years of experience in mining mining, metallurgical, and general industrial projects. He is a specialist in the treatment of industrial wastewater, treatment of feed water, water management, including reuse, recycle, storage, and water quality. And his work in the last decade has focused on integrating biological and chemical treatment in treatment chains. So with that, I would like to now turn it over to Miriam and Mark for our main presentation.
Hello all, my name is Marc Liberté. I'll start the presentation. Miriam will join me later. The agenda today, we're going to just briefly present Tracer SE, what it is, very briefly. Then we'll ask the question, why bother to remove Selenium? We'll do a very quick survey of existing technologies, and I mean very quick survey. I mean, there's way too much to cover in the time we have, but we'll just give a glimpse. Cover some new regulations that might be coming in Canada, and then we'll go into more details once we have all that background on the new Tracer SE technology, and we'll have questions at the end. This is a presentation that was given 2 weeks ago at the Mine Water Solution Conference in Vancouver. There is a companion paper that was published. The companion paper, you've got the link in there. You will also receive within 48 hours a link by email where you can directly download that paper. The paper goes into a lot more detail than what we can give in this presentation today. If you have any questions, also don't hesitate to contact either Miriam or myself, and we'll do our best to try to answer you. So with that, what is Tracer SE? Very briefly. So basically, Tracer SE, it's a way to remove selenium that combine biological reactors, MBBR, and we'll cover later on for those of you not familiar with what is an MBBR. For now, let's just say that it is a biological reactor where we do a reduction to selenite. We, after that, use surface complexation to remove the selenate and the selenium that is being trapped in the biomass. And finally, another biological reactor to reoxidize the remaining selenium into the water back to selenate. So it's basically a combination of equipment that is already in use in hundreds of locations, but it's a new approach and it has some distinct advantage that we're going to be covering. But first question is, why bother removing selenium? And actually, it's a very good question. So selenium, as you are probably aware of if you are listening to this seminar, selenium exists in a variety of oxidation states. In mining, actually in nature, it mostly exists as selenate, which is selenium +6, and selenite, which is selenium +4. It is commonly found with sulfur ore because selenium is actually very similar to sulfur. So if you have sulfides in the ground, it's likely that you have traces of selenium as well with the ore. And the chemistry of the selenium is actually fairly similar to the chemistry of sulfur. I want to add that the leading treatment technology that we use nowadays for removing selenium is the reduction of selenium to elemental selenium. So even if elemental selenium is not naturally present, or at least not in any significant concentration into the environment, the treatment process that is used, that is mostly used nowadays, does produce elemental selenium. It does also produce organoselenium species. As I said, this is not something that is naturally present, but it might be present in the effluent of a treatment plant that is based on the reduction to elemental selenium. Selenium is essential for life. There are actually a number of enzymes into your body, into my body, into the body of most living organisms that do require selenium to be working. It is also part of some amino acids, selenocysteine and sorry, I've got the blank on the other one, but whatever. There are two amino acids where selenium is also present. So it is essential to life, which means that the cells have mechanism to actually absorb selenium for the environment to make sure that that selenium is available for the enzymatic action that is required. That has a number of consequences. And one of the issue that we have with selenium is that selenium at the concentrations it is naturally present in the environment is not acutely toxic, which means that it's going to be very, very rare that there is water with enough selenium in there that you put whatever fish or species you can think of in the water and they're going to die within hours or days. However, what's happening is that selenium does bioaccumulate. And as it bioaccumulates, the concentration in the organism increase as you go up the trophic chain. So you see in the little graph that we have on the right there, you have the concentration of the water. It is absorbed by the algae. It is then absorbed by invertebrates. It's then absorbed by fishes, by bigger fishes, eventually by birds. And as we go up that chain, we have the concentration in the body that increase. And what we have seen in the last decades is the number of well-publicized events of fish and bird mortalities, typically stuff like salmonids, salmons, actually salmons, but in general, trouts and all fishes of that family, and grebes, which are basically a kind of a duck that is fish eating. So and there's been events, especially out west, where they've had been thousand upon thousand of birds or fishes that have died, and then they have died because of that bioaccumulation of selenium. Just going to cover very, very, very briefly the existing technologies, and as I say, I can't really do justice to this topic in like a couple of minutes, but just so that we have an idea there. Basically, there are well, at least two main approaches there. One is I'm going to call that the physico-chemical approach. And that's basically using stuff like membrane technologies, where you do a separation based on size, or ion exchange technology, where you do a separation based on the charge, or zero valent iron with in co-precipitation, where basically you do a reduction using metallic iron. The zero valent iron is the metallic iron, which does reduce the selenium, and where you do have co-precipitation. Those technologies, all of those technologies work, and I'm not going to say they don't work, but they all have various issues, which I'm going to cover on the next slide. We also have what I'm going to say is the leading treatment technology at the moment for selenium removal, which is reduction to elemental selenium. Basically, the idea is that elemental selenium is a solid. It is essentially completely insoluble in water, which means that if you can reduce seleniates and selenites, which is selenium +6 and selenium +4, to elemental selenium, selenium 0, you are producing a solid. And that solid can then be removed, and because there is no solubility, in principle, you could remove all of the selenium from the water. And within the biological treatment family, you have a number of variations, including active treatment, hybrid treatment like gravel bed, passive treatment, in situ treatment. There's all kind of various options that can be used. But at the end of the day, every biological treatment out there on the market right now is based on the reduction of selenium to elemental selenium. Now, the issues. Physico-chemical treatment has not found wide acceptance, and then there's a reason. There's a reason for that. Basically, membrane and ion exchange, they work, but you just displace the selenium. So basically, you do produce a concentrate, and then you have the same amount of selenium that you had before. Ion exchange, I'll be honest with you, if you have a smaller flow, can be combined with electrocoagulation, and actually, which works quite well because you can precipitate the selenium using electrocoagulation, and that's actually a technology that has been demonstrated in a number of plants. But it's not the technology that scales very well. So as the flow increase, you get a system that is becoming more and more complex, more and more costly, and eventually it simply become uneconomical. However, ion exchange with electrocoagulation for small flow is actually quite an attractive technology. Zero valent iron, which is the reduction of selenium on elemental iron, seems quite simple, but actually it's quite complex. There are a number of side reactions, including with nitrates. Nitrates actually compete with the selenium for the reduction of iron. It doesn't have a tendency to produce a lot of ferrous iron in the water. That ferrous iron is itself toxic, so must be treated. You have a tendency also to plug the media, so the media becomes solid and basically impossible. There's no more any capacity to flow through and can't really be regenerated. So it's actually a good idea, but quite difficult to implement in practice. I understand that there are a number of companies still working with zero valent iron. There are new formulation of zero valent iron that are out there in the market, and they seem to have solved some of the issue. But there's stuff like, as an example, the competition with nitrates, which is inherent in the design of this system. So at the end of the day, this, in my opinion, is going to remain limited to some specific cases, especially in the absence of nitrate in the water. Biological treatment, reduction of selenium to elemental selenium, it seems so neat, but there are a number of very, very practical issues with that treatment. First, kinetics are very, very, very slow. The first part of the kinetic, which is reduction of selenate +6 to selenite +4, is actually quite fast. But the second step, which is reduction of selenite +4 to selenium, elemental selenium 0, it's actually very, very slow. And that means if kinetics are slow, that you're going to have big reactors, and big reactors mean that you're going to have an expensive system. The second issue is actually probably even more of a concern, is that as you are reducing the selenium to elemental selenium, the mechanism by which bacteria do that actually produce a lot of organoselenium species. And those organoselenium species are what is going to be causing the toxicity in the water. And we've seen example where we had reduction of 1,000-fold in the concentration of selenium, but where the treated water was more toxic than the raw water because of switch in the speciation of the arsenic and the presence of those organoselenium species. New regulations. That's also part of the picture, especially in Canada. In the US, actually, I'll come back to US. Actually, we had development since that was written. In Canada, there is currently a proposal. It's not yet it hasn't not yet been published officially as the law, but the feds have proposed a coal mining effluent regulation that would require treatment down to 10 microgram per liter as a monthly average and 20 microgram per liter as in a gram sample. That's actually an issue because most treatment technologies right now, especially biological reduction to elemental selenium, have difficulties getting below 20 to 25 microgram per liter on a consistent basis. I mean, they may some days be at 10 or 5 even microgram per liter, but I mean, on a consistent basis, it is difficult because they also have days where they're at 20 or 25 or 30 or something like that. And so for them, it is actually quite difficult. What we're proposing today, we are expecting to be able to achieve 5 and 10. So 5 as a monthly average and 10 as in a grab sample. So we expect to be able to easily meet those regulations, and it's really a big plus for us. I'm going to go back to the US, and that's actually not in the slides because that's something that just happened 2 weeks ago. 2 weeks ago, the EPA, and I do apologize. Not I'm mixed up there. So, sorry about that. There are also applications for there are also regulation for selenium in the US. The regulation for selenium in the US are actually a little bit lower than what we have in Canada. I'm not sure how it is applied, however. So for it's something that will have to be follow up later on. And with that, Miriam is going to present in more details the tracer SC treatment system.
Thank you, Mark. It was really interesting. So, hi, I'm Miriam de la Durante. I will take over for the tracer Selenium application more specifically. So the tracer SC, what it is, the tracer SC technology, the main goal of it is to reduce the selenate to selenite and to stop there. So no further reduction, no production of elemental selenium or the less we can, and which will actually minimize the organoselenium production. The selenite, selenite, sorry, can be removed using surface complexation through a physico-chemical treatment. The surface complexation is the use of an insoluble salt, mainly aluminum or iron, for metal adsorption. So the main objective is to create aluminum or an iron structure, crystalline structure, while recirculating some sludge, metallic sludge, that will eventually, with the pH conditions, attract either heavy metals or oxyanions on the surface. In that particular case, we are aiming for the adsorption of selenium on the metallic surface to remove from the process. This is extensively used right now for arsenic, antimony, cadmium in mining water treatment. So this is something we worked with on regular basis. The main things we need to control here, it's the rate of recirculation to make sure that the sludge is mature enough to allow the surface complexation, the dosage of the insoluble salt, the metal, to make sure that there's enough surface available for the contaminant to remove, and the pH, because it is an attraction and adsorption, so you need to have the right conditions to make sure that your metals are attracted to your surface, and the right metals needs to be attracted to the surface to be efficient. So in resume, we take the selenate in the raw water, we reduce it in the biological reactor to have selenite, and then we remove the selenite in the precipitation reactor by a physico-chemical treatment with surface complexation to have an insoluble salt that will be removed within a solid separation sludge. So the blood flow diagram, Mark went briefly through it earlier on. I'll go a little bit more in detail here. So the mine water first goes to an MBBR for the reduction of the selenate or any other metals. It also works for arsenic. It also works for antimony and various oxyanion with different oxidation state. So there's a phosphorus source, there's a carbon source. The reduction of the metals is happening here. You can also have denitrification. It's a reactor similar to denitrification. In the application we first tested it, it was just simply a denitrification reactor that we use, and we saw the metal reduction right here. Then once the metals are reduced biologically in the MBBR, it goes to a precipitation reactor where there's a pH adjustment, some coagulation using aluminum or ferric salt. There's some surface complexation in there to make sure that the metals are rightfully adsorbed on the surface of the flux created. Then it goes to a solid liquid phase separation phase. So in that particular case, it's an active flow ballasted flocculation. So addition of polymer, we create flux with the metal precipitated in the reactor. Then we put some microsands polymer, it all glued together, and then the sludge go down, clear water goes out of the system. The sludge is partly recirculated back to the metal precipitation for the adsorption, for the creation of the crystalline structure for the surface complexation. And part of the sludge is simply extracted out of the system to be disposed. Just a quick notice here for the disposal. The sludge coming from a surface complexation system is not, it's not stable for a long period of time. It can be oxidized, change of pH can modify the adsorption of the metals, so it can create some release of metals. So it's important to really manage your sludge accordingly. And we do have solutions for the stabilization of these sludge, so it's not an issue. But this is not part of the webinar, but this is certainly something we are able to work with. So this is not a problem. It just needs to be considered at the end. The clarified water is still in reducing conditions, so it's still anaerobic. There's no air. Fishes don't like being in a water where there's no oxygen, so the water needs to be reox. We need to inject some oxygen back in the water to make sure it's not toxic. Also, since we are having a reduction, a biological reduction, we are dosing some carbon source. The carbon source, there will be a slight residual to make sure that the conditions are perfect for the bacteria as within the biological reactor. So it needs to be removed before going to the environment. So this is why there's a MBBR for reoxygenation. It's just a little MBBR reactor with a very fast kinetic to remove easily biodegradable carbon and to put oxygen back in the water. And we also found out if there's any traces of there will be a little bit of organoselenium produced within the denitrification reactor or the reduction in BBR. This organoselenium fraction will be mainly removed in the MBBR reax right here. So the concentration of organoselenium released to the environment is very slight compared to traditional selenium, biological selenium removal, because we are creating less and we are removing most of it in this particular step. Now, what is tracer selenium? As I said, it's a combination of a biological system, which is in that case an MBBR, a moving bed biofilm reactor. You can see on the right side, this is a picture of the lab study that we are presenting today. So the reactor here is the MBBR for the reduction of selenates to selenites. It also took into care of it also take care of the nitrate removal because there was some nitrate in the water. Once the biological reduction is completed, it goes through an active flow, which is a ballasted flocculation for removal of selenites to using surface complexation. And then there's a second MBBR to remove any remaining selenium to selenate. In here you see 3 reactors because in that particular project we had some nitrification to do upstream of all this. So it was nitrification, denitrification, and metal reduction followed by oxidation. This has been demonstrated in the lab, and it's currently we are in a patent application at the moment for this particular project, starting with the results we obtained, and we will present to you briefly soon. So just a quick introduction to what is the MBBR. It's the moving bed biofilm reactor. The main features of the MBBR is it's a proven technology. There's hundreds of installation, a lot of installations, nitrification, denitrification, COD removal, BOD removal, and some exotics. Some exotic other, there's some selenium removal, biological, traditional selenium removal using an MBBR, thiosalts, couple of applications. It's a fixed growth technology. It's easy to operate. It can operate at low temperature. Once it's correctly seated and the kinetics are all working, you can operate it as low as you want when the biomass is mature. You just need to prevent it from freezing because, well, little carriers in a block of ice doesn't do much, but it can operate. We've seen operations at as low as 3 degrees C in the northern Quebec. It has a high tolerance for TSS in the effluent because it's there's the bacteria are attached to the carriers, so the TSS just go through the reactor without impacting the biomass, and it's also resistant to flow variations for the same reason. The active flow, well, the active flow, we have a lot of active flows in many applications. It's an enhanced clarification process. It uses lamella tube settlings, microsand recirculation, and what is really important is the possible of the sludge recirculation. So we extract the sludge at the bottom, we remove the sand from the sludge, we can recirculate the sludge, we can reuse the microsand. So we don't have to spend the sand, it's just recycling in the active flow over and over. And we can recycle the sludge in the reaction tank upstream. It will help for surface complexation, but it can also help if there's any potential for scaling issues to scale, well, to create flux of the scaling agent upstreams. If we're talking about something with gypsum, can also help for, well, many applications. Sludge recirculation really helps to increase the capacity, the efficiency of the treatment. It's a very compact system. There's short retention time because the lamellas helps to have a very high surface area for the settling. So it's very compact, it's easy to operate, and it's very robust. You can start it in a matter of minutes, and it's fully functional very fast. So now, the main part everyone is interested in is the results of the tracer SC in an application, a lab scale application. The tests were done on a real mine water. So this is not a synthetic water. This is really, we received a tote of water from a hard rock mine, and we did lab testing to test this application. And these are the results we observed. The results I will present here today are after 4 months of stable operations. So the system was mostly at equilibrium. The only part that was not in equilibrium was the redox because of the manipulation we had to do in the lab. But I will just point out where it had an impact. But just keep in mind that the system was stable, and what goes in goes out. So there's no creation or just selenium that disappear in the nature. We really can say where the selenium is going. This is stable. So let's start with the raw water coming in the system. In this application, we're talking about 48 ppb of total selenium going in the process. We measured the total selenium go in the denitrification reactor or the reduction MBBR. We can find that there's no modification of the selenium total concentration, which is normal because there's nothing going in or out of the system that will explain more or less selenium. So this is a good start to see that we are at equilibrium right there. I'll go a little bit more in detail for those two results. So out of the 48 ppb in the raw water, 45 ppb was dissolved selenium. as selenate. Going in the MBBR, we saw that the dissolved selenium was 3.7 ppb. So most of the selenium in that particular reactor was particulate. So we measure it, but it wasn't dissolved. What
Just going out of the MBBR, you said going in, I believe. Going out of the MBBR, we had 47.8 and 3.7 dissolved. So basically in the reactor. Sorry to have interrupted.
It's okay. Thanks, Mark. So yeah, it's about 4 ppb in the MBBR, going out of the MBBR. If I just get mixed there, I'm sorry. So what we discussed a little bit, because these are from speciations we completed with the lab that is very, well, they've done a lot of speciation with selenium, so they're used to see those speciation and they have the knowledge for it. While discussing with them, we asked if it could be elemental selenium. We asked what could be the source of that. What we were told was this is not the signature of elemental selenium. So we believe at this point that the particulate selenium seen out of the MBBR is mostly selenium being accumulated in the biomass. It's probably just absorbed by the microorganisms, because it can be, I don't know how to explain it, but it's really that the selenium is absorbed in the biomass and not elemental, not organic, just absorbed. And then it went to the active flow. So the metal precipitation, surface complexation, and active flow. A measure was taken on the clarified water of the total selenium concentration. So we're down to 3.5 total selenium. Most of the particulate selenium is out, and some of the dissolved is removed at this point. And then we go to the Reox MBBR, where we can see a final concentration of 6 ppb of total selenium. This is where I told you that most of the system was stable, except the Reox. This is where we can see that it wasn't stable. Oh, sorry. This is mainly due because when we did the manipulation, the MBBR can be fed continuously. So there's always water going through the biological system. But when we need to get some metal removal using the active flow technology, this is not something that can be done continuously at lab scale. We need to do batch testing. So we need to accumulate water out of the reduction MBBR. And then this water is treated by batch, and then we need to take this water and pump it back to the Reox MBBR. So all of a sudden, the MBBR sees a different quality of water, and it has not been fed for a couple of days by the time we need to accumulate the water for the clarified water production. So all these little things will make that the Reox system is not stable, and that could be the cause of why we're not seeing something that is totally logic here, that we have production of selenium, which is mainly probably because the system was not in equilibrium and some biomass just went loose with the rush, and we had some selenium. The concentration is so low that just a little bit of selenium will show here. Now, we will talk about dissolved selenium, which is where, well, the dissolved and organic selenium, which is the part where we are mostly interested with, because this is the selenium that is dangerous for the environment. So going in the raw water, there's no organic selenium. It's below the detection limits. In the biological reactor, we're talking about 2 ppb of organic selenium. Organic selenium is all the species that they can measure that are clearly stated as organic selenium, as well as everything that is an unknown species. We were told, discussing with the specialists of the external lab, that these unknown species have a signature really close to organic selenium. For this reason, we decided to include it in organic selenium, but we're not sure these are actually organic selenium, but we are being more conservative in the analysis right here. So there's a very slight production within the MBBR reactor. Then we go to the surface complexation and to the active flow. We can see there's a removal of there was a removal of selenite as we were aiming. This is not shown in this result, but you can see in the papers with the complete speciation that this is removed as expected. But what we could see that is really interesting is that we observed some removal of selenomethionine at about 90%, selenosulfate at about 80% removal, and selenocyanate about 30% removal. So there's a slight removal, there's a removal of organoselenium. Sorry. Mark, can you take over? I will just start to cough like crazy.
Yeah, sure. So we can see there is actually some removal of organoselenium in that stage. What is also interesting is that as we're going to the reactor, even as if you saw on the previous screen that we had an increase, a little bit 2 ppb increase in total selenium, there was actually factor 3 reduction of organoselenium species in that reactor. You have an accompanying paper, all the detailed speciations with all the analysis and everything. So if it's of interest to you, you can go there and you can trace what's happening with all the various species. But we can see that we add basically the same concentration because at those level, 0.18 ppb in the raw water and 0.23 ppb in the discharge, the treated water. It's about the same thing. So on the net, there was no increase of organoselenium into the process. And for us, that's actually a huge difference compared to the conventional system. You could see that if we had treated only the water, going from the first reactors, we're actually at 2 ppb. So we reduced that. Even if this is not as reducing as a conventional process reduction to elemental selenium, we still have a very, very good reduction of organoselenium in that treatment chain. Next slide, please. So next steps, where are we? So we have demonstrated the process in the lab. Actually, we did demonstrate that. We presented the results on from the hard rock mine. We also demonstrated the process on the coal mine effluent with very similar results. So we demonstrated that in the lab on 2 different samples. We realized at this stage that it's a lab demonstration is not sufficient to go to full-scale application. We believe that it is very, very promising. We are looking to run an on-site pilot for 6 to 12 months. We had actually found a partner, actually a coal mine, that was interested in working with us developing that coal mine, but the promoter decided to stop the development of that new mine. So we are finding ourselves a little bit in a bind right now. We have a process that works. We're looking for a partner to help develop that. We are also in contact with various government agencies and trying to develop this. We would like, once we have something on site, to test both the sludge management, because as Miriam mentioned, it is actually quite an important part of any selenium removal process. How do you make sure that selenium does not come back into the environment once you stop your treatment long term? And would like also to generate enough water to do some chronic toxicity testing. It's simply not possible at lab scale to generate enough water to run any kind of significant chronic toxicity testing. And this is where we are. And I'm going to stop here. I think we ran a little bit over schedule. Jill, I think we have time for some questions.
Yeah, Thank you, Mark and Miriam. Yeah, if you want to go to the next slide there, and we will kick off our Q&A session. So thank you both for that. And with that, I will kick off Q&A just so we can try to get through at least a couple of these. I know everybody's short on time, but we'll try to get through as much. Question for you here is talking about the lab scale testing. What was the flow rate of the lab scale? And then a follow-up question on that also, or secondary question is, was an active flow used or just jar mixing and settling?
I can't recall the exact flow. It was in the order of 5 liters per day, but I might be off by 1 or 2 liters per day. I do apologize. I think it's in the
It's
paper.
about 5 liters per day.
Yeah, I think it's around 5 per day. At that scale, 5 liter per day, it's not possible to use a real active flow. So basically, it was I call that semi-batch. So basically, accumulate water, run a jar test, take the water from that has been treated in the jar test, put that in the tank, and then feed that into the Reax reactor. And that's actually the part where we didn't do that on a long enough period to be at equilibrium. That's why the Reax results are a little bit off. Obviously, when we go on site, we'll like to have the full system, including the active flow and everything.
Great. Another question that we've got here is, you mentioned a significant reduction in the footprint of the treatment compared to a traditional approach. What is the order of magnitude of such reduction?
Well, obviously it's going to be case specific because it depends on the amount of nitrate and selenium and everything you have in the water. Roughly, I'd say that footprint.
About 10
Probably,
times.
yeah, 10 times. I was going
In
to
2
say 10.
applications we've looked at, it's about 10 times for the footprint.
Yeah, and in volume of media, because obviously the volume of media is the cost, you're probably at 20, 30 times smaller, something like that.
Yes,
Maybe
what you
40
need,
times smaller, something like that.
it really depends. What you need to remember is that in all application for selenium removal, you need to remove your nitrate beforehand. The big difference with the tracer is you don't need the selenium reduction biological reaction there. So you're just removing this reactor completely. You're just working as if you have your denitrification and you're good to go.
Great, thanks. Another question that we've got here as well is talking about the retention time within the MBBR, and what exactly was that?
Again, I mean, okay, the conventional system has retention time that's depending again on the concentration, probably I would say a day, depending also on temperatures. It's also temperature dependent. We found that in the application we tested, we're more at the scale of maybe 4 hours. Miriam, would I be completely off?
Somewhere around that, it really
Yeah.
depends of the concentration going in the system.
But again, MBBR is always designed on load, so not on flow. So if you have a stream that is relatively concentrated, you're going to see higher retention time because what you're interested in is the load, the kilograms or the pounds going in. If you have a very dilute stream, then you will simply be passing more flow to have the same load. So the question of retention time, it's kind of tricky to have a general answer to that.
We're mostly talking about kinetic here. The kinetic for the tracer SE is very fast compared to the kinetic used for the selenium reduction to elemental selenium.
Great. Yeah, just to follow up on that too, I think this question kind of ties right into that statement there, but there was a mention of kinetics at the beginning of the presentation. How is the kinetics of this system compared to biological treatment systems?
100 times faster, something like that. And again, go back to what Miriam said, it's important. In both cases, you need to remove nitrates because any biological system will, when you do the reduction, nitrates will always go first because they simply, it's more efficient for bacteria to do denitrification first. That part is the same. But once nitrate have been removed, the tracer SC process is probably 1 time faster than the reduction to elemental selenium. Did I answer the question, Jill?
I believe so. If not, we'll follow up directly, or they can follow up directly with us, and we will try to answer that as well. So, couple more questions here. I think we've got time maybe for a couple questions here. So, what are the main differences in operation of the tracer SC MBBR, tracer Selenium MBBR, I should say, compared to traditional biological selenium removal processes?
Miriam?
Yes, the main difference is when you're working with a biological removal of selenium, you need to have the reducing conditions within the reactor needs to be very well. The ORP needs to be very low. When we're working with the tracer SC, the conditions are similar to what we are seeing with denitrification. So we need the ORPs are higher. The conditions, this is less reducing, the environment is less reducing in the MBBR for the tracer than from the classical MBBR.
Also, because the kinetics are faster, the retention time will be lower. That's the other aspect. But it's very similar. To be honest with you, it is very similar, just a question of degrees. So a little bit less reducing condition and a little bit lower retention time.
Great. And I've got a couple questions here just on pH levels. So I'll see if I can kind of combine these questions here. But talking about or sharing the different pH levels of the different phases of the treatment. And then a secondary question on pH as well is, what was the pH level you were able to maintain to remove the selenium in the lab work?
In the MBBR itself, the reducing MBBR, you are at circumneutral pH. I mean, it can vary a little bit. pH is not super important for the biological reactions. I'd say we were running between 6.8 and 7.5, so 6.9 and 7.5. Miriam, would that make sense?
Yeah, this is not an issue. There's not much of a pH adjustment for this particular reactor.
What was the second part of the question, Jill?
For the physico-chemical removal.
Physico-chemical, selenium removal by surface complexation is best done at about neutral, slightly alkaline conditions. Surface complexation is affected by ionic strength of the in the water, so obviously the condition might change a little bit. Also, aluminum has a slightly lower pH than iron. Aluminum is more effective at a little bit lower, a little bit more on the acidic side, but you are at neutral a little just bit on the alkaline side for that surface complexation reaction.
And Mark, this is when we only remove selenium. Most of the time we have more than one metal, so we will optimize for the removal of most of the metals to make sure that we have the best performances at the smallest footprint.
Great. I think we've got one more, or time for one more question here, and I apologize if we didn't get to all the questions here, so we will follow up directly with you, but just in the essence of time here. During the commissioning phase of a tracer SE process, how do you plan on growing the right bacteria in the denitrification reactor to develop the right conditions for the selenate reduction?
You want me to go, Miriam?
Yeah, sure, go ahead.
Basically, we found that in the environment you have most of the bacteria that are required to do this. As I said, selenium is naturally present in the environment. It is necessary to life for most organisms. So most bacteria have the mechanism to actually handle that. We found that if you provide an environment where the bacteria can develop and attack media and everything, they will eventually grow a population that is able to do the reaction we need. Veolia does not, as a rule, use specially cultivated bacteria or bacteria that have been modified or whatever it is. We found that there is usually in the environment enough bacteria to actually give a good efficiency into the reactor. We also found, and it's quite interesting, that as the system get older, as the bacteria, as the system is kept in operation for longer, the system become more efficient and more resilient. And we believe that it's because you have more and more species that actually grow on the in the reactor. And as you get into a more complex system, as you have more and more bacteria and archaea and all those things there, you get the system that is actually better able to handle variations. Because if suddenly the condition change and you have a bacteria that is no longer optimum, it's likely that in an old system that has a couple of years of operation, you've got other stuff that can actually do the reaction you're looking for.
Great. Well, thank you both for that very informative presentation today. And I do want to thank everybody for joining us as well. And I do appreciate you staying on a few extra minutes to go through that Q&A session. If we did not get to your question, we will follow up directly with you. And with that, that concludes our webinar today. I do want to ask if you would be so kind again to take that survey as soon as the webinar concludes. We do appreciate any and all feedback, and for those of you who do fill that out, excuse me, you will be entered into a drawing for a chance to win that $25 Amazon gift card. So if you are the lucky recipient of that, we will follow up directly with you. And then, as Mark mentioned earlier in the presentation today too, you will receive an email directly from us within about 48 hours or so with a link to that white paper for those of you who are interested in reading a little bit more on this specific topic. So with that, that concludes our webinar today. Thank you, Mark and Miriam, and to all of our attendees for joining us. Thank you.